So let's say you could just melt down the Earth's crust into this giant, massive pool of molten rock. What happens when it starts to cool down? What kind of minerals pop up? And in what order? Well, that's exactly what we're going to break down right here.
And that right there is the central mystery, isn't it? I mean, if magma is just this one big soup of melted stuff, why doesn't it all just freeze into one solid block at the same time? Why do we get this incredible variety of rocks when it cools? It's a really good question.
Well, the answer to that puzzle was actually figured out way back in the early 1900s by a geologist named Norman L. Bowen. You could say he literally wrote the roadmap for how igneous rocks are born.
Okay, so to really get what he discovered, we've got to start where he did. We need to go right inside the magma itself, before any of that cooling begins.
See, magma isn't just hot rock. Think of it more like a super complex chemical soup. It's this wild mix of all these basic building blocks, especially things like silicon and oxygen. And when those combine, they form what we call silicate minerals. These are, for real, the main ingredients for pretty much all the rocks on Earth, and they're all just jumbled together at these insane temperatures. And here is the absolute key to everything. At really high temperatures, certain minerals are perfectly happy. They're stable. But as that temperature starts to drop, those same minerals, they become unstable. So they have a choice. They either have to change into something new, or they just stop forming completely. This simple rule is the engine that drives this whole process.
So what Bowen figured out is that this cooling process isn't just one straight line. It's more like a fork in the road. The magma actually goes down two totally different paths at the same time, which famously creates this classic Y shape.
All right, so here are our two paths. On one side, you've got the discontinuous series. That's where whole new minerals pop up and replace the old ones. Then you've got the continuous series, where it's the same mineral, but its chemical recipe just kind of shifts as it cools. Okay, let's break that down.
Okay, so this is that changing minerals path. Think of it like a chain reaction. First, at the super high temperatures, the first mineral to form is olivine. But as things cool down a bit, olivine suddenly becomes unstable. So what happens? It actually reacts with the leftover liquid magma to form a completely new mineral, pyroxene. Then, as it cools even more, pyroxene gets replaced by amphibole. And finally, at even lower temps, amphibole turns into biotite mica. See? Each step is a total do-over, creating a brand new crystal structure every single time.
All right, now let's hop over to the other branch of that Y. This side of the story is a lot simpler, but believe me, it's just as important.
So, on this path, we're only dealing with one mineral family, plagioclase feldspar. When it's really hot, the crystals that form are packed with calcium. But as things cool down, sodium atoms that are still floating around in the magma start to swap places with the calcium atoms inside the crystal. The basic building block, the structure, stays the same, but its chemical makeup just smoothly shifts from being calcium-rich to sodium-rich. It's basically the same mineral, just with a slightly different flavor, if you
Okay, so eventually, the temperature drops so low that both of these paths have kind of run their course. And this is where they meet up, right at the bottom of that Y, to form the very last group of minerals. And here are the final players. After all the main action is over, what's left of the magma finally crystallizes into potassium feldspar and muscovite mica. And the very, very last thing to form? Quartz. So why is it last? Well, it's because quartz needs two things: a lower temperature and a whole lot of silica. And guess what? That's exactly what's left in the pod at the very end of the whole cooling process. So, okay, that's the theory. But why does any of this matter? Why should you care? Because this isn't just some boring list of minerals. This is the actual blueprint that explains all the different igneous rocks we see all around us every single day. And this brings us to what is maybe the biggest idea of all, the one thing that a lot of people miss. This is what connects this whole scientific series to the real world. It's really this simple. How that magma cools controls everything. It decides which minerals are going to form, what order they form in, and how they combine. It's the reason a black volcanic rock from Hawaii looks absolutely nothing like your granite countertop. Think about it. The minerals that form first at those super hot temperatures, like olivine, they're packed with iron and magnesium. That's what gives us dark, heavy rocks like basalt. On the flip side, the minerals that form last at much cooler temperatures, like quartz, they're super rich in silica, and they create light-colored rocks like granite.
This is so cool because it means that geologists can just look at the minerals in a rock and basically read its life story. They can tell you if it cooled down super fast near the surface or if it took its time deep underground. The series tells you exactly what kind of rock you're going to end up with.
You know, if you had to boil this all down to one single sentence, this would be it. Bowen's reaction series shows the order and conditions under which silicate minerals crystallize from cooling magma. It's basically the official rulebook for how to make rocks.
So, the next time you see an igneous rock, I don't care if it's a little piece of gravel on the ground or a giant mountain, I want you to remember what you're really looking at. It's not just a rock, it's a story. It's a complete history of how that magma cooled down, totally frozen in time.